So very good morning to all of you. Now, currently we are in the last session of last dot solving session of this particular course, Introduction to Material Science Engineering. We went through the 12 weeks, and subsequently for each of the week we have solved the questions. We solved the doubts which was there. Now at the end, now there is a the session is designed in a way that you should be able to ask the questions, all the questions which you are facing problem from the week 1 to the week 12, and whatever the doubt you have, that we are going to solve today. Let's quickly have a look on the list of the content that has been covered in this course. They are as follows. We discuss about the crystallography, where we discuss that regarding the symmetry, and for example we discuss about the various type of structures stacking. For example, FCC, BCC we structure, HCP we discussed, and also we discuss about the for example like what the crystal is made up of, that is lattice and what and their symmetry. Okay, we discuss how we can represent the direction and how we can represent the plane. Okay, we know the direction of single direction we represent in the square bracket, and the plane we can find it in this particular type of bracket, while the family is represented by this type of brackets. We discussed we went through the Miller indices, and we saw that how we can find the Miller indices for the direction and how we can find the Miller indices for the plane. I have two questions in the subsequent slides, where we will solve the how we can find the direction and how we can find the plane Miller indices. Okay. Later on, we discuss about the structure of the solid. For example, NaCl, CaCl we discussed. So and diamond cubics is there, hexagonal close pack there. Then we move to the defects in the solid. There we discuss about the zero-dimensional defect, that is the point and the vacancies, point defects. One-dimensional dislocations, two-dimensional defects, surface defects, and the three-dimension which are void. Then we move to the phase diagram, there where we discuss about the eutectoid, peritectic, and larger extent we spend time on the iron carbon diagram, which is very important from the engineering perspective. Now for any phase diagram, we saw that a diffusion should happen. Then only the phase transformation will take place, and for that we discuss about the diffusion. There we discuss about the Fick's first law and Fick's second law. Okay. Due to this diffusion, the phase transformation will happen, and we saw the TTT diagram. For us, it was more important to study the eutectoid. Eutectoid reaction, which is invariant reaction, and this is the one which will lead to the like heat treatment. So whenever we were doing the heat treatment in the iron carbon diagram, we saw that we have to go above this particular eutectoid reaction temperature, and we have to hold them for a particular period of time, and then a different cooling rate will lead to the different microstructure. A process can be annealing, normalizing, and quenching. Then after this phase diagrams, we went through the mechanical behavior of the material. There we discuss about the slip plane, slip directions, and how dislocations will behave. We have also discussed about that the Schmidt's law, Schmidt factor. Okay, so those things we have discussed over here. At the end, which was last week, week 12 content, we discussed about the fractures. We discussed the ductile fracture and brittle fracture. In this, we also discuss about the creep mechanism. We discuss about the fatigue. So these are the, on an average, the list of the content that has been covered in this particular course. So yesterday I have received a couple of questions from you, Omkar. So we are going to solve those questions. Apart from those questions, is there any other questions regarding this particular course? Please let me know. Okay, since there is no doubt, let's go and try to solve a couple of questions which was given by you, where you are facing a problem in this particular type of to answer these questions. The question number one: which of the following lattice do not have a threefold symmetry? The question is threefold symmetry. N is equal to 3. N is equal to 3 means by how much rotation we have to do? Theta will be equal to the 360 divided by N, which is 360 divided by 3. It will come out to be 120 degrees Celsius. Sorry, 120 degree. So the rotation of 120 degree should give me the symmetry. Like, now for example, I have a triangle. Let's say I'm making a figure like this. An angle between them, each of them, is nothing but a 120 degrees Celsius, 120 degree. Now let's say I'm denoting this line as a 1, 2, and 3. Now I'm trying to rotate them in a direction. Let's say clockwise or anti-clockwise, doesn't matter. Let's say I'm rotating them in the anti-clockwise direction by the amount of 120 degree. I'm performing this n-fold symmetry. What will happen? 1 will go to the 2. 2 will come to the 3. And 3 will come to the 1. We can see the initial orientation and the final orientation, they are exactly same. So this is symmetry. This operation is a symmetrical operation. This geometric operation which we did, rotation by the 120 degree, is a symmetry operation. Similarly, the question is asking which of the following lattice do not have a threefold. First one is a cube. We know that in the cube, there is a direction which is 1, 1, 1. About this particular direction, there are three folds is there. So if I rotate the cube about this particular axis, what is going to happen? It will form the threefold. The symmetry will be preserved. Let's see this cube in a much more detail. Since it is cubic and centered, so the atoms will be there at the corners. Along with the corner, we'll have the atom at the face center. Now our aim is to see along this particular direction. Okay. If I try to see there is a stacking. Okay, let's not discuss about that. I'll just make things complicated. If I see along this particular direction, what will happen? See, let me draw this particular atom over here. This atom will be just below this is one atom. Here it is an atom. Here it is an atom. If I try to project them in the three dimensional, I am trying to project them in the 2 dimension. What will happen? What will I get if I am seeing from here? I will get something like this. So this particular line I have drawn over here. This particular edge is over here. This particular edge is over here. And the bottom one is over here. Since I am seeing from this direction, I am seeing from this particular direction, like you can consider this to be the arrow. if I try to see, this atom will fall just below this particular atom. Okay, they will fall just below this atom. Now you can see that in between these two, there is an atom over here also. There is an atom over here also. So if I try to draw in between these two, I have this. So let me draw this one with the black color. Now this particular one, there is one more direction which is lying in between these two directions, which is this and this. Okay, in between them. So it will come something like this. And also I draw this one, I draw this one. Now between these two, we have this atom. Between this direction and this direction, we can see there is an atom over here. If I try to draw this one, it will come somewhere over here. Now consider the case one. I am trying to apply now threefold rotation over here. Threefold rotation means the rotation by the 120 degree. What will happen? This line, let me donate the line A, B, C, D, E and F. This A will rotate and come to the C. This is 120 degree. Again the C will rotate and come to the E. This is 120 degree. And this will rotate and come to over here, again 120 degree. What about B? B will also rotate and come to the D. D will rotate and come to the F. And F will rotate and come to the P. So what we will see after this particular rotation, we will again get the same figure which we have drawn. A which was over here, now it will come to this. C will come to E. And E will go to A. Okay. B will come to the D. And D will come to the F. And F will go to the P. So we can see A, B, C, D, E. Sorry, this will be F. Right? F will go to the B. Here also, so more or less what we have got, the same structure. The initial and the final remain exactly same. So this is a symmetry operation. And cube have this symmetry. One of the most important fact one should remember is that cube have four of such symmetry. Okay, not only along 1 1 1, also along other direction. For example, 1 bar 1 1. Okay, 1 1 bar 1. Like this, cube will have total of 4 3-folds. Total of 4 axes will be there, about which our cube will rotate and will have this type of symmetry. So with that we can say, the question is that which of them don't have? Cube is definitely it is having. Hexagon. Hexagon is like this, right? Now about this particular axis, if I try to rotate, hexagon also have the 6-fold symmetry. Sorry, 3-fold symmetry. This will rotate and it will come over here, again it will come over here, and this will come over this particular. Hexagon also have the 3-fold symmetry. To be more precise, hexagon also have the 6-fold symmetry, not only rotation by the 120, even the rotation by 60 degree will preserve the symmetry. Okay, so here it will have 6-fold, and the one which is having 6-fold will also have the 3-fold. Okay, let's say I'm telling that I'm rotating by 60 degree, so and I'm getting the symmetry. It is also equivalent to saying that okay, if you rotate by 120 degree, which is multiple of the 60 degree, so it will also have. So A is having the 3-fold. Hexagonal is having the 3-fold. Trigonal, what is trigonal? Sorry, trigonal. take a cube take a cube and stretch it along the one of the body diagonal. Let's say our body diagonal about which we are stretching is 111, this particular direction. So along that particular direction we will definitely have a threefold remaining. See what we say, we told that here cube has the four threefolds, right? More will be there. 1 bar 1 and 1 1, so this 4 will be there. Let's say I am stretching my cube along this particular direction. What will happen? Remaining all will get disturbed. They will not have, no longer will have a threefold. Only this one will have threefold. So the trigonal will have only one threefold. But the thing is that it is having a threefold. So this is also having the threefold. Orthorhombic. Now the problem with the orthorhombic is that or I can use the other people also. Yeah, this one. Here A is not equal to B and not equal to C. I made it wrong. I should have made more precisely, but it's fine. A is not equal to B, it will not equal to C. So the angle is no longer one, like we we will only have a two-fold symmetry about this particular thing. Threefold is not there in the orthorhombic. Also, threefold is not there in the tetragonal. Tetragonal has one four-fold symmetry. Okay, so our answer will be, this is the incorrect, and we wanted the one which is don't have, so option B is the right answer. Okay, so Omkar, is it clear, this question number 1?
Yes, sir.
Great. Let's go to the next question which you pointed out. Fill in the blanks. A dash axis pass through each lattice point of a 2D square lattice. 4-fold, 2-fold, 6-fold, none of the above. Let's focus on this particular part. 2D square lattice. Let's make the 2D square lattice. This is one of the square. We can translate it in other directions. I will add one more. Now, let's focus on this particular square lattice, this particular section. If I rotate, let's say this is my axis about which I am rotating. By how much amount I should rotate this so that this point will coincide over here. Since this is a square lattice, what we'll get? We'll get something like this. So the initial and the final will exactly remain same. The rotation should be by the amount of 90 degree, right? So if I rotate this entire lattice about this particular point by the amount of 90 degree, I will get the symmetrical structure. Take any square, for example, let me make small square. Okay, I have one single crystal dioxide. Let's say this is my square lattice. Oh, it's not even visible. Leave it. I can directly take this itself as a square. So this is my square, one of the square. I can club more number of square across this and I can make the entire lattice. Now the point is that if I rotate this entire, let's say, consider this, one more is there over here, and similarly one more is there over here, and one more is there over here. Now about this particular point, if I try to rotate, what I will get? I will get the same axis, same symmetry, which was previously was there. So the entire rotation I have to do is, for this particular point is 120 degree, sorry, 90 degree. So about this particular point we have 4-fold. So about this particular point also we have a 4-fold. One more axis, it's very easy to remember that. See these 4 points which I just draw, it is these particular points. And now what about this particular thing? If I try to rotate about this axis by 90 degree, I will get the same thing. Again I rotate by 90 degree, the symmetry is preserved. Okay. So not only about the lattice points, also inside I have a 4-fold symmetry. Okay, so with that we can say that a dash axis pass through the each lattice point. So for the each lattice point, we know what is passing about this particular lattice point is a 4-fold symmetry. Option A is the right answer. Now, two-fold. One can argue that a two-fold is also right because if I rotate by 90 degree and let's say I'm rotating twice, 2 times, what I will get 180 degree. And also you know that if you rotate by 180 degree, the entire thing, this will come over here, which will be preserved, and this will come over here, right? Two-fold is also the correct answer in this particular case. But if the question is only MCQ, not MSQ, in that case I will only answer 4-fold. The reason is that the two-fold is incorporated in 4-fold. Okay. So two-fold is also the subset under the 4-fold. We usually answer the one which is having the highest symmetry. So for example, hexagon, I told you that hexagon have 6-fold, which is also, we can say it is also having a 3-fold. Rotate 3-fold, rotate 6-fold 2 times. 6-fold means 60 degree. 3-fold means 120 degree. Rotate by 60 degree, then again rotate by 60 degree, you will get 120 degree. So 3-fold is a subset of the 6-fold. But what we say in the hexagon, we usually say that it is having the 6-fold, which is the highest symmetry. We usually specify the highest. So in the case of MCQ, if it is, we will go for the option A. Now let's go to the C, 6-fold. No, it doesn't have 6-fold. 2D square lattice doesn't have the 6-fold. 2D hexagonal lattice have 6-fold. Okay. Put this back. So with this, we have solved this question number 2, and where we found that the option A here is the right answer, that is 4-fold. So each of the lattice point, the axis passing through each lattice points are this. We found that it is having the 4-fold. So Umka, is it clear? Question number 2. See, when we are talking about the symmetry, silicon diamond. just a minute. Whenever we talk about the symmetry, the lot of visualization will be required. You have to imagine a lot of things in your head. So the thing is that you just make your square lattice. You just make your square lattice and see what kind of symmetry it will follow. For example, you know, if you have a triangle, equilateral triangle, the angle between them is 60 degree. Let's say about this particular axis you want to rotate. So you tell me by how much amount you have to rotate so that this triangle will again come back to this. What is the minimum rotation we have to do? Not 60. If I rotate by 60 degree, what will happen? The triangle which I will get, it will be something like this. If I try to rotate by 60 degree. So see, you have to rotate, you're rotating about this particular axis. So this point should come over here. This point should come over here. You have to rotate by 120 degree for the triangle. If you rotate by 60 degree, what will happen? You will get something like this. So your initial orientation is this, but final orientation you will get like this, which is not equivalent. Again rotate by 60 degree. Then you will get like this. So this is the thing. Now for example, rectangle you have. Now about this particular axis you have to rotate. So by how much amount you should rotate that you will again get the rectangle. 180 degree, right? Very good. If you rotate by if you rotate by 90 degree, you will get something like this, which will be the vertical rectangle. So this is just a visualization that to what extent you can visualize. Triangle, we saw that we have to rotate by 120 degree. What about the hexagon? Instead of making a triangle, I make a hexagon. So by how much amount should I rotate? I have to rotate by amount of 60 degree. Then only I will get the hexagon. Okay. Same. Yeah. So there is no shortcut for this. You have to visualize. Symmetry need lot of visualization. So option A here is the right answer. Okay. Let's go to the next question. Question number 3. This was a question which you asked, that what are the Miller indices of a plane that makes intercept A, B, C axis equal to the 1 angstrom, 2 angstrom, 3 angstrom in the tetragonal unit cell, tetragonal crystal. So there is a plane. Let's say this is A axis, B axis and C axis. Here it is making 1 angstrom. 1 angstrom, 2 angstrom, here it is 3 angstrom. Our aim is to find the Miller indices of this particular plane. Now, let's do a very simple question before we go through this particular question. I am making a tetragonal unit cell. Here this is A, this is B, and this is C. Our aim is to find the Miller indices of this particular plane which I am drawing now. This is A axis, this is B axis, and this is C axis. What will be the first step? The first step will be we have to find the intercept with each of the axis. So with this particular axis, how much the intercept? Intercept is 1 of A. This one we have 1 of B. And in the C direction we have 1 of C. Now what we'll do? We'll drop this A, B and C, we'll write only 1, 1 and 1 over here. Now we'll take the reciprocal. Reciprocal of 1 will be 1 only, and then again here will be 1 and here will be 1. And with this we will get the Miller indices of this particular plane. Then we'll put them in this type of bracket. So first thing is that we have to find the intercept in terms of A, B and C. This is our aim. What is given to us? The absolute value. In the x direction it is 1 angstrom, in the b direction is a 2 angstrom, and in the c direction it is 3 angstrom. The value which is given to us, it is in the absolute value, not in terms of a, b and c. So we have to make them first in terms of a, b and c. What we'll do, we'll divide them by a, this will divide by b, this will divide by c. So now we'll get the intercept in terms of a, b and c. So this is our intercept in a axis, this is intercept in the b axis, and this is the intercept in the c axis. Now what we'll do, now we got the intercept. So we got this particular thing now, right now. At present we got this. Initially what was given is this, where A, B and C were already incorporated in 1 angstrom, 2 angstrom and 3 angstrom, because these were the absolute value. We have to find the value in terms of we have to normalize them. So here what I did, see here I found the 1 times A, 1 times of B and 1 times of C. What I did, I divided by A, I divided by B and I divided by C. So whatever the intercept I got, I normalize them with respect to that particular axis, and whatever the value I got later on, I keep on solving them. Similarly, I did here. The intercept here is 1 angstrom, 2 angstrom and 3 angstrom. Now I will normalize them. I will divide them by A, B and C. Now let's see what we will get. One divided by A, 2 divided by B, and 3 divided by C. Information is given to us, it is a tetragonal. In tetragonal, no, A is equal to B, which is not equal to C, and so the relation between C and A is given to us. C is equal to the 1.5 times of. Now let's put all the value and try to see what we did. From here we went to this. What is the next step? We have to reciprocal them. Now we have to reciprocal it. A divided by 1, B divided by 2 and C divided by 3. Now our next step will be to make them in the smallest possible integer. Let's substitute their values. A divided by 1, B I can write as B is equals to the A, so I will write A divided by 2. In the place of B I will write A. Now C I can write in terms of A, which is given to us. C is equals to the 1.5 times of A divided by 3. In all of them I can see the factor of A is there, which is common, so I will eliminate them. I will write 1 over 1, 1 over 2, 1.5 divided by 3, which is 1 over 2 again. At the end I got this and this. My aim is to find the smallest possible integer. So what I will do, I will multiply entire by 2, 2, 1, 1. So this is the plane I will get. We followed the same procedure. The procedure says that first we'll find the intercept. Intercept was already given to us. Those intercept, we will normalize them with respect to that particular axis A, B and C. This is also I did over here. After that, next step, we took the reciprocal. Okay, we took the reciprocal. Once we got the reciprocal, our entire aim was to find the smallest possible integer, and few relation was given to us. If the question will talk about, instead of tetragonal, it will talk about the orthorhombic, in that case A is not equal to B and it is not equal to C, and so the relation between them will be given. A will be equal to the 2B and it will be equal to the 4 times of C. So again, it is just for this particular sake, so that you can find the smallest possible integer. You can find that In the dot solving session, week 2, I have solved the questions which is based upon the orthorhombic, which is difficult than the tetragonal one. Okay, comparatively, little bit, because none of the values are equal. So you can go through that also. So these are the procedure that we have followed. Please let me know, Omkar, if it is clear. Okay. With that, we have solved this question number 3. Let's go to the next question, question number 4. Which of the following rotational symmetry is absent in ABC stacking of a closed back sphere? Okay. Which of the following rotational symmetry is absent in ABC closed back? See, first of all, closed back, since it's specifying closed back, there can be two closed back. It can be cubic closed back and it can be hexagonal closed back. Hexagonal closed back have the stacking of AB. Cubic closed back have the stacking of ABC. And it is given that our question that we are concerned about ABC, so we got that it is cubic closed back. That is face-centered cubic. Now, in the FCC, we just now discussed that in the case of FCC, what we have, let's draw the cube. Our concern, let's say this particular axis we have discussed. And here we saw that this axis have threefold symmetry. The axis is 1, 1, 1. In this folder direction, we have threefold. So first thing is clear that this particular one, it is having the threefold. Now, threefold it is having. What about two folds? Two folds are, fourfold is there or not? Let's talk about the fourfold first. So about this particular axis. Okay, take a square. That's what I have shown just now. For example, let's say that this is my square and this is my cube. Imagine that this length and this length are same. Consider that this is a cube and I am seeing from the top. About this particular thing, about this particular axis, I have fourfold symmetry, right? So with that, we can say that it is having the fourfold over here. Also, whenever the fourfold is there, also twofold will be there, but here, when we are talking about the cube, the two folds are along this particular axis, which is connecting these two opposite edge 1, this particular edge. Across this we have twofold. So it has fourfold, it has twofold. What it doesn't have, it is a sixfold. This is missing. So which is absent? So our right answer will be the option D. One should remember that sixfold in the entire 7 crystal system, only hexagonal is having. So whenever the sixfold part is coming into the question, or whenever you're talking about the symmetry crystallography, it is present only in the hexagonal crystal system. So with that, we have solved this question, and the answer is sixfold is not there in this particular stacking.
Okay, sir.
Okay, great. So with that, we have solved these 4 questions. Now let's go to the next question, question number 5. Identify the crystal which is having the twin bond ring. Twin bond. Twin bond ring mean that about a particular plane, the stacking will be exactly symmetrical. For example, here I'm writing A, B, C, A, C. So this A will come over here and this B will translate B, and then here it will be C, D, then A again, then B again, and then C again. So here can be any stacking. It can be here, let's say here it will be, let's say here it's a C. So about this particular stacking, about this particular plane, what we are getting is a mirror. It's like putting the mirror over here, this entire stacking will be reversed. So this is our aim to find that. This is a twin bond stacking. Now let's go to the, first of all, twin boundary is also it's a fault. Okay, it's a defect. Now let's go to the first one. First one is saying that ABC, 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 again A, then B and C it will go. Here there is no defect. It is following the perfect tracking of the cubic close pack which we just discussed, ABC, ABC, ABC and ABC. So it is not having any defect. No twin boundary. Let's go to the second one, AB, 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 AB. So this is following the HCP stacking, right? So again, there is no fault in this. Perfect stacking of the ABC, ABC. Now the third one, ABC, ABC, BAC. Okay, now we have to see. ABC was there, perfect. Now about B, there is a fault. Now since there is a fault, let's try to see about this particular fault. Is the mirror is there or not? C, here it's a A. B, here it's a C. So mirror is not there. For the twin boundary, there should be the mirror. So this is again not the twin boundary. Now the last one. A, B, C, A, B, C. Then again here it's the fault. Right? ABC, ABC followed, but now here B came where it should be the A. So now about this particular fault, let's see the mirror is there or not. We can find that the mirror is there. See here, see here. Okay. A, B, C, A, B, C. Okay. Is there anything wrong in this, my question? Let me see whether I wrote the right question which you sent me. C, A, B, A, B, C, A, B, C, B, C, and B. A, B, C, A, B, C, B, C, A, and B. So about which? B, A, B, C, A, B, C. About this, a fault should be there. This is reflected. So instead of this, what should be there? It should be B over here, and here it should be the A. Yeah. So this question is from the NPTEL, right? The assignment question it is. Let me just check the first one, the third one, A, B, C, A, B, C, B. So there is a fault. About this one, A, C. If I consider this to be the fault, this is B, this is A, then this is C, and this is B. Okay. Yeah. So one more thing, like, so this is not the case. Now the third one you see, once we will see again. Once we should go from here to here, and one we should go from here to here. Now let's see this particular one. A, B, C, A, B, C, B, C, B. B, C, BC, and now B and C. Okay, so here it's a now we are going in the reverse direction. BC, BC, B. Here it should be the C, which is a fault. It's not there. So about this somewhere. Okay, this is right. This is right. This is right. So if I see this question, A, B, C, A, B, B, A, C, B. So if I see about C axis, about this particular thing, what I will get is a mirror over here, and then this, and then this. Is the right answer C in the question? What has been given in this question? What is the right answer? Okay. This is stacking fault defects, so it should be around the week 6 maybe. Week 6 is a diffusion. Defects we have discussed in which of them? Third one is the right answer, right? Yeah. So that's what we have. So because the one which you sent me, there the answer was D even. So this is not the correct because we are not getting the mirror. What we got the mirror is in this particular third one, where we can see that if I try to draw ABC and A, B, C, B, A, C, B, consider this particular one. This is a fault. So what we'll get is about this, there is a mirror. A is reflected over here, C is reflected back, and then again B is reflected over here. If we keep on proceeding, A will be over here. Okay. So the right answer here is option C. Okay. So the entire thing is that about one of the stacking, about one of them, entire thing will be mirrored in the case of twin bond. And this is how we have to identify. So is it clear, Omkar? Great. With that, we have solved this question number 5. Let's go to the next question. I think with this, your questions was over. I made few couple of questions, but before that, you also had a question doubts in the iron carbon diagram. Let's discuss that. Okay. So what we can do is, so here we have the iron carbon diagram where on the y-axis we have the temperature and on the x-axis we have the composition. Here we can see at different temperature. For example, 725 we are getting the eutectoid reaction, which is a solid, which is austenite, has been converted to the ferrite and cementite. Later on, when we went to the high temperature around 1150 degrees Celsius, there we can see the eutectic, where a liquid is converting to the two of the solid. The point to be noted that eutectic, whenever we are discussing IC, is at the end, it is talking about the liquid. So the initial phase is liquid and which is converting to the two solid. Here we can say that eutectoid here in initial phase is also the solid and it is converting to the two of the solid. So whenever IC will come, one of the phases will be the liquid. And this is the difference where the eutectic and eutectoid will differ. A solid is converting to the two solid and the liquid is converting to the two solids. Now, when we went to the higher temperature, 1493, there we saw the peritectic reaction in that a delta ferrite and reacted with the liquid and it is giving the austenite. Okay, so the solid is reacting with the liquid and giving the another solid, which is the austenite. So these are the three invariant reactions that we have discussed in the iron carbon diagram. Also, very important factor is that this we are calling the eutectic. This mean that the easy melting. So the see we can see that one of which is the melting point over here. We can see that the most easy, the lowest temperature at which we can melt the entire either the steel or the cast iron. So the cast iron we can melt around the easiest melt, the smallest, the lowest melting point is 1150 degrees Celsius. If we go above, will the temperature is keep on increasing over here, okay, right? So these are the list of the reactions and the important things to note it down. Also, about this is cast iron and this is steel. This is something which we have known in the class. So these are the list of the thing in the iron carbon diagram. Also, it is I told in this particular week when we were discussing about the iron carbon diagram that we need to memorize, we need to learn these values also, which is very important. That is 0.8, 0.002. At what composition the entire phase diagram will keep on changing. Okay, so these are the temperature and the point which we have to remember. And the phases, austenite, here the mixture of the austenite and the cementite will be there. Here the liquid and cementite will be there. Okay, so the entire phase diagram. It should be in our head. We have to memorize this. It usually happen that with the time when we keep on working on this phase diagram, we will get that. So Omkar, let me know what doubt you had in this particular phase diagram so that we can have a discussion further. Okay, okay. Uh, I know it's little difficult to remember. So, so first, usually you should remember about the eutectic. Let's say you are talking about the eutectic reaction, invariant reaction. Here, what we saw that a liquid is there. Okay, we will denote by L. It will convert to the two solid phases S1 and S2. One usually represent alpha and beta. Okay, so the liquid is converting to the two phase alpha plus beta. So here one liquid is involved and the two solid has been produced. It is like you are keep on lowering the temperature. What is happening? Solidification, but this is invariant reaction where the reaction will first complete. Now let's go to the eutectoid. These reactions are reversible. We can go in the opposite direction also. So that's why the professor usually use this particular sign. Okay, if it is not there, see we have mentioned that it's for the cooling. If you heat it again, these two solid will again back to the liquid. Okay, so these are reversible. Eutectoid, a solid one, will convert to the two solid S2 and S3. We usually write gamma is converting to the ferrite and cementite, right? So this is the eutectoid reaction. Now when we go to the peritectic, here alpha, which is sorry, here which is delta iron will react with the liquid and it will produce the austenite. So here one solid is going to react with the liquid and it is going to produce another solid. Okay. So this is a peritectic reaction. Also remember that when this particular let's say liquid we are talking about, the liquid has at this particular point, liquid has certain composition, right? But this liquid is breaking into the two different compositions. Like let's say in the liquid the carbon composition was something over here, let's say it is around 4.3, but when it break and it will form the, for example here, did I made any mistake? Liquid alpha, here it's right, perfect. So whenever it will liquid will break and it will form two solid phases, there one of the composition will be lower in the carbon content and another will have the higher carbon content. Okay, So this is how we will be in between them. Now, here also we can see when we were talking about the eutectoid, our composition, let's say starting with the point 8, now it will breaking into the two phases. One is ferrite, another is cementite. We can see the composition of the ferrite, which we usually find using the tie line, is lower than the point 8, and the cementite is higher than the point 8. So it will always be in between. Now here, if I try to zoom this particular one, what I will get, whether it's visible, no, it's visible. So here we can see that this point is the composition of the ferrite. Okay, the delta ferrite which is going to react, and this is the composition of the liquid. Okay, which is, see, 0.1 was the delta ferrite and the composition of the liquid was 0.5. What it produced? It produced the cementite, sorry, it produced the austenite having the composition in between them, 0.1 and 0.5. So this is how the entire reaction will take place. So yeah, so Omkar, any doubt in this particular thing? Peritectic, eutectic, and eutectoid. Okay. Omkar, if you don't have any doubt, please can you mute yourself? I think I'll do that. Let me mute. Clear, Omkar. Omkar, if you don't have any doubt, can you mute yourself? Like, you do the background noise, there will be. Yeah. Fine. Okay, let's go ahead. Let's go to the next part, question number 6. The stability of the austenite dash will decrease in the temperature below 725 degrees, 725 degrees Celsius. Everyone, we have already went through the class. Please feel free to answer this question. The stability of austenite will decrease in the temperature. If I keep on decreasing the temperature, if the temperature is decreasing, if I'm going below 725 degrees Celsius, then what will happen to the stability of the austenite? It will be more stable, the stability will increase, or the stability will decrease, or it will remain unchanged, or increase and then decrease. See, we know that when we are going below 725 degrees Celsius, the austenite, which was initially there, now it will try to convert to the ferrite and cementite. Lower is the temperature, more is undercooling. More is undercooling, more is the tendency for the phase transformation. Okay, so the driving force G, delta G, which is driving force, will increase with more undercooling from 725 degrees Celsius. So keep lowering the temperature, you will increase the driving force. Okay, so with that we can say that the stability, since it has more driving force to transform austenite to the ferrite and cementite, the driving force is more over here, so the austenite is less stable. It has more tendency to form ferrite and cementite. So with that we can say that the stability of austenite will keep on decreasing as we decrease the temperature below 725 degrees Celsius. Clear, guys? If any doubt in this particular question number 6, please let me know. Okay, great. Since there is no doubt, let's move to the next question number 7. This is something which we keep on discussing starting off this particular session. The crystal system is given to us and we have to match them with the column B. Feel free to respond in the text in the chat box if you find the answer. Regarding the triclinic, triclinic will match with which of them? Triclinic have, we know in triclinic A is not equal to B, not equal to C, alpha, beta and gamma, they are not equal with each other. It has no special symmetry. So with that, we can match the first one with the B. Very good, Omkar. Now, second one, monoclinic. For the monoclinic, we know A is, okay, very good. A single twofold is there, right? Very good. The option A here is the right answer. For monoclinic, we know that A is not equal to B. It is not equal to C. Okay. And alpha is equal to the gamma, which is not equal to the beta, and beta is not equal to the beta is not equal to 90 degree. Okay. So now with that we have answered. Now what about the tetragonal? Tetragonal is going to match with a single fourfold axis. Very good. Option E is the right answer. It has one single fourfold axis. Hexagonal. This is something which we have discussed. So hexagonal will have which of them? Option D. Very good. A single sixfold axis will be there, which is also about the C axis. In hexagonal, we have A, B and C axis. About the C axis, we will have the sixfold symmetry. Now the last one, cubic. Cubic is going to have perfect. It is going to have a 4 3-fold symmetry. Okay. So let's write the answer. 1, 2, 3, 4 and 5. The answer is B and then A, E, D and C. So this is the answer. With that, we have solved the question number 7. If any doubt, let me know. If not, let's go to the next question, question number 8. Identify the direction that lie in this particular plane of FCC crystal. So, see, I'm trying to cover all the questions. It's like I'm trying to cover to certain extent the question which is covering from week 1 to the week 12. So which law we are going to apply? Anyone can answer this. We have to find the directions. Which direction is going to lie on this particular plane of FCC crystal? What we can do? How we can find this particular thing? We have learned in the class that Weismann law. If a particular direction u, v and w, it is lying on in a plane HKL, then it will satisfy this equation HU plus KV plus LW is equals to the 0. This is UVW, this is HKL. Okay. So let's try to find them. Yeah, so first one, let's go to the first one. 1 multiplied by the 1 plus 1 multiplied by the 1 again plus 1 multiplied by minus of 2, which is equal to the 1 plus 1 minus of 2, which is equal to the 0. Since this is satisfied, the first one will be it is going to lie, this direction is going to lie in this particular plane. One can do geometrically also, but again, there will be we will require the more of the visualization, but it's doable, it's not that difficult. Let's go to the second. The B, 1 multiplied by the 1, then again 1 multiplied by 1, and then here it's a 2 multiplied by minus 2. When we will do this calculation, what we will get is minus of 2 additional. Okay, it is not 0, it is not going to satisfy this. What about the third plane? We'll do the same thing. 1 multiplied by 1, which is 1, minus 1 multiplied by the plus 1, which is minus 1. 0 multiplied by minus 2, it will be 0. So we will get here the answer is 0. Option C is the right answer. It is going to satisfy. Option D, when we will do this, again the multiplication part, what we will get, the answer will be 1. It is not satisfying. So whenever this type of question will come that a particular direction is given to you, and the question is that whether it will lie on a particular plane HKL, here we have to apply the Weismann law. Okay, this type of question you can expect in the upcoming exam of NPTEL this course. Okay, if any doubt in this question number 8, let me know. If not, let's go to the next part, question number 9. Very simple, but also very important. These are the designation. The list of the brackets are given to us, and we have to find which of the among this, which of the Miller indices it is going to represent. Square bracket UVW. Option 1. It is going to match with which of them? A, B, C, or D. We know the square bracket UVW, it is going to match with the single direction. It represents single direction. Okay. While this type of bracket, it is going to represent the family of direction. Also note that whenever in this type of questions, the directions is always represented by UVW and the plane is represented by HKL. Okay. So there is no way that we are going to make a mistake in the HKL and making them into the matching them with the direction. Now, the round bracket HKL, it is going to be, it will represent which of them? The single plane or the family of plane? Option A, very good. It is going to represent the single plane. And option C, the third one, is going to represent the family of plane. Okay, so we can write the final answer. It is D, A, B, and C. See, always remember when we are talking about the direction and we are talking about the plane, let's say single direction. Single direction will be by the square bracket, while the family of direction will be by the this type of bracket. Single plane will have this bracket, family of plane will have this bracket. Okay. Very important. Must remember. Okay. Any crystallographer, any metallurgist working in this particular symmetry, trying to understand, they should always remember this. Okay. With that, we have solved the question number 9. Any doubt, let me know. If not, let's go to the next question. Question number 10. I think this question has been asked in the quiz. The question is that we have to find the projection representing diamond cubic structure. Okay, the question is diamond cubic structure. Both open and the shaded circle are the atom of the same kind, and the number next to them shows the height from the projection plane as a fraction of the unit cell h. So, among this P, Q, R and S, which of them is going to represent for the diamond cubic structure? This is the question. Let's try to answer them. We'll make a diamond cubic structure. Diamond cubic structure is the FCC plus we have the additional carbon atoms will be there. The motif is made up of the 2 carbon atoms. Among that, one is at the FCC lattice, another is at the location 1 by 4, 1 by 4 and 1 by 4. Now let's draw one cube, and there we will try to visualize. I made the FCC. Along with the corner, there will be the atom at the faces. Okay. Now important thing, there will be atoms. So all of them are the carbon atom. What is the body centered? Body centered will represent by the fraction 1 by 2. 1 by 2, 1 by 2. Okay. So if I want to go to the body centered from here, I will go 1 by 2 in the A direction, in the B direction and in the C direction. I will land over here, which is just in front of the this particular 0, 0, 0. So from 0, 0, 0, if I take the origin, I have to go half in the x direction, half in the y direction, and half in the z direction. Now here, the carbon atom is also there at the 1 by 4th, 1 by 4th, and 1 by 4th. What it means? In the x direction, I have to go by the amount of 1 by 4, b direction 1 by 4, and the c direction 1 by 4. Right. So let's say this is my origin. This is representing O, O, O. And let's say this is representing 1 by 2. Body centered 1 by 2, 1 by 2, 1 by 2. So in between them, I will have a carbon atom which is at the 1 by 4, 1 by 4, 1 by 4. So in the x-axis, it is 1 by 4th, we have to move. Y-axis, we have to move by 1 by 4th. And the z-axis, we have to move by 1 by 4. So I will get an atom over here, in front of this. Also, I will get an atom in front of this. I will get one atom just in front of this and in front of this. And they all are inside, and considering their corners, they will be at the location 1 by 4, 1 by 4, 1 by 4. Now seeing from the top, let's only talk about the red atoms for a time being. I'm seeing from the top what I will get, what the projection I will get. I will get the corner atoms. I will also get this face centered atom will be over here. And this body centered atom, this side of body face centered atom will be over here. Right? And backside face centered will be over here. Now the thing is that seeing this particular projection, one cannot tell that this and this, whether they are at a different height or not. The one which is at the corner, we are not going to specify their height because we already know they will always be at the 1. Now what about these face centered atoms? Okay, this one. It is at the height of, from the C axis. If we see along the C axis, it is at the height of 1 by 2. So here I will write 1 by 2. Here I will write 1 by 2. Here I am not going to specify. The reason is that this is lying at the height of 1. Okay. Only will specify the one which is between 1 and 0. Okay. Here also, this atom is representative of this particular atom. Okay. The back one. So here this is also 1 by 2 and this is also 1 by 2. Now my aim is to know about this particular atom. Considering this to be the origin, this is the body, I have to go 1 by 2, 1 by 4 among this and 1 by 4 along this. So I will get an atom somewhere over here. This atom I will get somewhere over here. But its height, if I try to represent along the C axis, along the C direction, the height is only 1 by 4. Right? So here I have to write 1 by 4. Just now about this, what about this one? This is also at the same height. This is also at the 1 by 4th. This one, they will come over here and this one will come over here. But their heights are different. See, this is at the 1 by 4. This is at the height of 1 by 4 from the top. If entire is 1 and this is 1 by 4, so from the bottom how much is the height? It is 3 by 4. So here I have to specify 3 by 4. Here I have to specify 3 by 4. This is how one have to make the projection. I know that this is a little difficult to visualize, but once you know at what position they are lying, then you can project and you can write their values. We not specify the values which were at the 0 and the 1. This atom is representing this. Also it is representing this because they will fall just one below the another. This one is representing this one along with this. Okay, so on and so forth. So I hope it is clear. So now with that we can answer that. This is 1 by 4, 1 by 4, 3 by 4, 3 by 4. So option A is the right answer over here. This is 3 by 4, 3 by 4. No, we will not get. just below the another. They will always be opposite. See, 1 by 4, 1 by 4 will be opposite. 3 by 4, 3 by 4 will be opposite to each other. This is incorrect. Let's talk about this. 3 by 4, 3 by 4 opposite to each other. 1 by 4, 1 by 4 opposite to each other. This is perfect. This is the right answer. The last one, 3 by 4 is adjacent to the 3 by 4, which is not the case. It is not going to happen. So with that, we have solved that the two projections are correct. This is this and this one. One can say that why we only got this type of projection, 1 by 4 was here and 1 by 4 was here. Then why you are answering this? Why 3 by 4? Take this, rotate by 90 degree. So now what we'll get, 3 by 4 is this, 3 by 4 is this, 1 by 4 is this, 1 by 4 is this. It's just the way of seeing things. One can see the square like this. One can also see the square like this. Okay. So initially, let's say this was my 1 by 4 was here and 1 by 4 was here, and 3 by 4 was here and 3 by 4 was here. If I rotate, I will get the opposite. It's just the way of seeing. Okay. So with that, we have solved this question number 10. Any doubt in this question, guys? Question number 10. I know it's a little difficult. If you are facing difficulties, please let me know. I will again try to explain it. Okay, great. Since there is no doubt, let's go to the next question, question number 11. It is match the pair. Triangular void, tetrahedral void, octahedral void, and the cubic. They will correspond to the which of the radius ratio? Let's start with the first one, triangular. 0.72, 0.115, 0.155, 0.224, 0.413. So the triangular, we know that option B is the right answer, right? Very good, Omkar. So we have to put the void is over here. Okay. So if the triangular will be only stable if we are having the radius ratio greater than 0.155. What about the tetrahedral? Second one. Tetrahedral is going to match with the C. Very good. 0.225. Octahedral 3 is going to match with the D. 0.414. And the last one, cubic. It is the highest one. Alright, very good. A. 0.732. Which is A. Always remember this trend, 0.155, 0.225, 0.414, 0.732. These values we should remember. Okay. With that, you have solved the question number 11. Any doubt in this, guys? Let me know. If not, let's go to the next question, question number 12. Again, this question I took from the defects part. I hope it's visible now. Yeah, now it's visible. The enthalpy of formation of the vacancy in aluminium is given to us. At what temperature would the vacancy concentration become double that at 0 degree? Okay. Let's say at 0 degrees Celsius, at temperature is equal to the 0 degrees Celsius, we have the vacancy concentration to be the N. We want to find the temperature at which the vacancy concentration would become the double of that which is at the 0. Right. So our aim is to find this particular temperature. So the vacancy concentration at particular temperature T, it is equal to the 2 times vacancy concentration which is at the particular temperature of 0 degrees Celsius. How we can find? Small n divided by capital N will be equal to the exponential of minus of Q divided by R times T. We can substitute them over here. So in this particular case, it will be capital N times exponential minus of Q divided by R times of T. The T is unknown. It will be equal to the 2 times, which is at the 0 degree Celsius. It will be given by the exponential of minus of Q divided by R T. 0 degree Celsius, I can write them in the Kelvin at 273. Again, N will be there. So from here, N is cancelled out. The value of Q is given to us 67.54 kilojoule per mole. Whenever we do the calculation, we'll convert kilojoule per mole to the joule per mole by multiplying by the 10 to the power of 3. Very easy. We know in this particular equation what is the unknown? Unknown is the temperature. Q we know, the value of R we know, 8.314. Now we can solve for the temperature. Right. So one equation, one variable, which is T. I'm not going to do that calculation part. My aim is to tell you the method how we can do that. Okay. So by solving this, we can do that. Let me tell you, these questions I have already solved in the previous dot solving session. I'm just putting it over here so that we can have a quick remind that what are the questions that are relevant from our exam perspective or the course perspective. Okay, very good. If any doubt in this question number 12, let me know. If not, let's move to the next question number 13. In a binary alloy, the number of phases present in equilibrium at the eutectic point is dash, and that at the eutectoid point is dash. Okay. Number of phase. Let's say eutectic we are talking about, liquid will convert to the solid alpha plus beta. Here it's alpha, liquid plus alpha, liquid plus beta, here it's beta. The question is still talking about the eutectic point, which is this. At this particular point, how many phases are present? Liquid is converting to the alpha and beta. We are talking about the equilibrium. Liquid is there, alpha is there, beta is there. Very good, Omkar. So number of phases are 3, which is liquid, alpha and beta. What about the eutectoid? Instead of liquid, it will be some other phase. Let's say it will be the gamma over here. So what will happen? Gamma will convert to the alpha and beta. Again, it will be 3. Yeah, perfect. So we will have the 3 phases at the eutectoid point. Okay. Even for the peritectic, which we have discussed, there we discussed that the delta is reacting with the liquid and it's forming the phase austenite. Here also we have total of 3. The important thing is that we are talking in the binary alloy right now. Okay. So ternary will have, again, one more thing will be added. So let's not discuss about that particular right. So here we will have 3 and 3. With that, we have solved the question number 13. Any doubt, let me know. If not, let's go to the next question number 14. Find the phase fraction of alpha ferrite in a plain carbon steel with 0.1 weight% carbon at a temperature just above this eutectoid temperature. Take the eutectoid composition of steel as 0.8. Okay. We have to find the phase fraction of the alpha ferrite in a plain carbon steel. And we are just above the 725 degrees Celsius. Let's draw the phase. Let's draw the phase diagram. The eutectoid composition is given to us as 0.8. Find the phase fraction of the alpha ferrite in the plain carbon steel with 0.8 weight% carbon. So we are at this particular composition where the carbon composition is 0.1. And this we know. Let's say since it's not given, we can write the one which is given in the phase diagram. Let me show you. 0.08, sorry, 0.02. Okay, so this is 0.02. And we are at what temperature? Our temperature is, we are just above this particular detector temperature, somewhere over here. Okay, just above. Our aim is to find the phase fraction of alpha ferrite. What kind of rule we apply over here? In order to find the phase fraction, we discuss about the phase diagram. When we want to find the composition of a particular phase, we use the tie line. And when we want to find the fraction of a particular phase, there we use the lever rule. Okay. So right now, our lever says that we are between 0.8 and 0.02. Our composition is 0.1. Here it's alpha and here it's a cementite phase. Okay, so this is alpha plus austenite. So now what we can do, we have to find the ferrite phase, right? So what we'll go to the opposite arm. Ferrite is this side. We'll go to the opposite arm. What we'll do, 0.8, this divided by the entire, we'll get the phase fraction. 0.8 minus 0.1 divided by 0.8 minus 0.02. Right? This is the fraction of alpha phase. If you multiply it by the 100, you will get the in percentage. So we will remember that whenever we have to find the phase fraction, and when we are talking about the phase diagram, especially for the binary, it is much more easy, lever rule. Okay, just use the opposite lever arm of corresponding to that phase, and then you will get the divide by the entire lever, you will get the particular answer. Okay, so with that we can solve the question number 40. If any doubt in this question, let me know. If not, let's go to the next question, question number 50. I have total of 2 more questions. If the activation energy of the diffusion is given to us, okay, at what temperature will the depth of diffusion be 10 times that at the 25 degrees Celsius for the same diffusion time? Similar type of expression will come which we did just before this particular question. Diffusion depth x, we know, is directly proportional to the root over d times t. Right? We have to find the temperature at which the depth, which was initial depth, and the final depth will be 10 times more than that at the 25. 10 times at the 25 degrees Celsius. We have to find the temperature corresponding to which can lead to this depth. Again, the diffusion time is for the same diffusion time, so T is constant. So one more factor we have removed from here, T. So x is directly proportional to the root of D. What we can write? X as 25 degrees Celsius divided by a depth at particular temperature which I don't know, it should be equal to the root over D of 25 and D of the temperature which I don't know. How we can do that? We know D is equals to the D naught exponential minus of Q upon RT. Pardon guys. So now here I can substitute over here in this thing. See, x25 divided by x over t, I can rearrange and I will get 1 over t. Now for this particular case, d of 25, so d naught exponential minus of q divided by r t, that is we will write, always will write in the Kelvin, multiply by 298. the whole divided by d naught exponential minus of q divided by r multiplied by the t. When we solve this, we'll get the temperature in the Kelvin. If the requirement of the question is in the degree Celsius, you can just reverse them by minus of 275 degrees Celsius, minus of 275. Now in this equation, d naught got cancelled. R we know the value, Q, the activation energy is given to us. Again, I will say the same thing, convert it to the 10 to the power of 3 joule per mole. This will cancel out. The value of R we already know, Q we know. One equation, one variable, and variable is T. Now we can easily find this. Okay. So this is how a question will frame. It can also happen, like, see, we have, for this equation, 3 variables are there. So the question can play in the 3 different way. One can also say, the question can also talk about the same depth. Instead of saying the same diffusion time, it will talk about the same depth. For the same depth, at particular temperature, the thing was happening at 5 hours. Now let's say now we increase the temperature. How much time will it take for the particular depth to happen? Okay. So in that case, so we know that the question is going to play with 2 of the variables. Okay. Keeping one as constant. Either d can be the constant, either t can be the constant, or x can be constant. For our case, the time was constant. Okay. So with that, we have solved this question number 15. If any doubt, please let me know. Okay, great. Since there is no doubt, let's go to the next question. Should I solve this question? Okay. Before question number 16, let's go to the question number 17. Okay. The question is very easy. We have to find the Miller indices for this direction. Okay. The cube is given to us. So what are the steps that we have to follow? It is written over here. We have to choose the origin as one of the point. I will usually choose the tail. This is my origin. Second, we have to choose the coordinate axis. Let's say this is my A direction, this is my B direction, and then this is my C direction. Okay, so the entire length along this is A, this is B. See. Coordinate of the other point we have to find now. No, we can easily do that. What about when we are going in the A direction? We are going entirely back. That is minus of A we went. We came to this particular point. Now we have to move in the B direction, and B direction again we have to move entirely. So again we have to move over here, but see, the direction was this. We are moving in the opposite direction, so it's a minus of B. And now we are moving in the C direction, but in the C direction we are moving only by the amount of C by 2, not entire C. So it will be the C by 2. Also, we are moving in the up direction, not in the downward direction, so it is a plus. We can remove A, B and C, right? So minus of 1, 1 by 2. We can make them in the smallest possible integer, so it will be minus 2, and 1. Bar we represent at the top, negative will represent as a bar, and we can put them in the square bracket. So this is my direction. One can also say, one can multiply them entirely by the minus 1, and you can say that it will be 2, and 1 bar. So both the answers are correct. Okay, both are correct. You will find I was going through the doubt solving, that Q&A forum. There I found that one learner was discussing about a plane. Let's say the answer is 1 bar 1 0. What he was getting is 1 bar 0. So they both are exactly same. It's just that they are multiplied by the minus 1. Okay. In the similar way, these are exactly same. So if you are getting let's say this, instead of choosing this as origin, you choose this particular as origin. Then you will get this answer. I choose this origin, I got this answer. But though both the answers are exactly correct. Okay. So with that, we have solved this question number 17. Let me know if there is any doubt. If not, Let's go to the final question. And this question is very important. It will be little difficult. It will be difficult in a particular way. Okay. Let's try to solve it. We have to calculate the number of atoms in a critical nucleus when the solid copper formed by homogeneous nucleation at this temperature using the following data. See, we know that, for example, I have a liquid. In my container, I have entirely liquid. I went below the melting point. What will happen now? Inside this liquid, a nuclei will start to form. Okay. The question is saying that this nuclei has formed. You have to find the number of atom this nucleus is having. This was a question which was asked in the last year assignments. Okay, and it's a very good question. Let's try to answer this. What we'll do, first we'll find the radius of this nucleus form. We have to find the radius. In the class, there was one formula which I wrote. Smaller, the radius of the nuclear form will be negative of 2 times of surface energy times melting point divided by delta Hm and delta T, which is undercooling. Delta T is equal to the T minus Tm. Okay. Now, we have all the values. Okay. We have all the values. You can see the delta Hf, the enthalpy of formation, is given in the joule per meter cube. The surface energy is given in joule per meter square, and the whatever the values are given to us, they are all in the SI unit. Only the temperature we have to change from degree Celsius to the Kelvin, and that we can do. Now let's try to answer this. Negative of 2 times gamma, surface energy is given. It is 177 multiplied by 10 to the power of minus of 3 joule per meter square. Okay. Multiplied by the melting point. Melting point is given towards 1083 degrees Celsius. We have to add 273 so that we can make them in the Kelvin. The whole divided by, okay, delta Hf, sorry. So here we will write 1628 multiplied by 10 to the power of 6 joule per meter cube. So we don't need to bother about it. Okay. The units are going to get cancelled. Multiply by the extent of undercooling. Undercooling is T minus Tm. At what temperature? 102 degrees Celsius minus of melting 1083 degrees Celsius. So even if I convert to the 273, the difference is not going to change. Okay. So what I will get? 83 minus of 2 is 81. And since this is smaller, I will get minus of 81. So difference here is 81 with a negative sign. Now you can see this negative and negative will cancel, and the radius of R will be the positive quantity. We have to solve this. Let's do it quickly. I am little bit more comfortable in this particular calci. 2 multiplied by the 177 multiplied 10 to the power of minus 3 multiplied by 1083 plus 273 divided by 1628 multiply 10 to the power of 6, and again we will multiply them with the 81. So what I have got, the radius form will be 3.64 into 10 to the power of minus of 9. What will be the unit? All were in the meter square, meter cube, meter square. So what we will get? It's in the meter. So we got the radius. So the nuclei has formed. Let me take one more page. The nuclei has formed. And we found the radius of this particular nuclei. And the radius was it is obtained is 3.64 into 10 to the power of minus of 9 meter. Our aim is to find the number of atom in this nuclei. See, this nuclei has formed, it will have some crystal structure. Okay. What is the volume of this particular nuclei? Volume will be 4 over 4 by 3 pi r cube. And this volume will be equal to the, let's say n is the number of unit cell. In this we have this, let's say this is the unit cell. N is the number of unit cell and V is the volume of the unit cell. V is the volume of it. So if we multiply them, this will be the entire, the number of unit cell, the volume of one unit cell, we will get the entire volume. It will be equal to this volume. So from here we can find the number of unit cell. How we can find the V? Few information will be very hidden in the question. That is, we have to track copper. After melt, solidification of copper is happening. So copper, we know, copper have the FCC crystal structure. So how we can find the volume of the unit cell? Volume of the unit cell will be the A cube, lattice parameter to the power of cube, and multiplied by the A cube will be equal to 4 over 3 pi r cube. You can see the value of A is given to us. The value of lattice parameter is given to us and multiplied by the 3.614 into 10 to the power of minus of 10, the whole to the power of cube will be equal to the 4 over 3 pi r cube. This is my r. What I will do, I have to use it again. I'll store this particular value of r in A. Okay, so I stored the value of r in A. Okay, I made a mistake with storing while storing the value. Anyway, I'll write it again. So let's find the value of n. N will be equal to the 4 multiplied by the pi multiplied by the r cube, which is 3.64 into 10 to the power of minus of 9, the whole to the power of cube, divided by 3 multiplied by 3.614 into 10 to the power of minus of 10, the whole to the power of cube. We will solve this now. Multiplied by the pi multiplied by something to the power of 3, and that is the r to the power of 3, 3.64 multiplied 10 to the power of minus of 9, and then here 3 multiplied by this to the power of 3. Okay, 3.614 multiplied by 10 to the power of minus of 10. So this many unit cell is there. 4279.8. Okay, I will not take the fraction into account, 0.8. What I will do, 4 to 7, 79, right? I will make it 80. So this many unit cell are there. One unit cell, how many atoms for the FCC? Can anyone answer this? In one unit cell of FCC, how many atoms are there? It is 4. Right? One atom will be at the corner, 3 atoms will be at the face center. So total we will get the 4 number of atoms. So from here we can find the number of atoms corresponding to this many unit cell, which will be 4280 multiplied by the 4. Okay. Let me multiply by 4 and I will get the answer to be the 17119. So this many number of atom of copper will be there in this formed nucleus. Okay, so that's why it was little difficult, but once we know the procedure, it's easy. The important point was that the hidden information which is given by the word copper, okay, which is FCC, and FCC unit cell has the 4 number of atoms in one unit cell. Okay. So with that, these are the list of the things which I wanted to discuss. We started our discussion with the questions which was given by the Omkar, And once it was over, all the doubts we have cleared, and then we discuss about the couple of questions which I have made. So before I end this session, which is final last session of our office, I would like to ask you, do you have any doubt in the today's session that we have discussed, or anything that we have discussed till now in entire course? Please feel free to ask me. So this was a question by the Omkar regarding the twin boundary and regarding the stacking faults, regarding the symmetry. And here we discuss about the tetragonal and how we can do the Miller indices. Okay, I think you might have made wrong answer in this particular questions, but we can follow the procedure. Go through the doubt solving session of the week 2. We have discussed about this part in much more detail. So this was the list of the questions that we discussed, and these are the concepts that was covered in our course Introduction to Material Science and Engineering. Okay, great. Okay, since there is no doubt, we can wind up today's session, and if you face any problem, let's say you want to contact, then you can do on that Q&A forum. Also, I will write my email ID. You can contact me on this particular email ID. Okay. So with that, we can wind up today's session, and I wish all of you a very best for your upcoming exam of NPTEL. Okay. Okay, guys. Bye bye.